Yeah, so my name is Joe DaSilva. I'm a GPU solutions architect at AMD. I'm one of the rare breeds in this community who, you know, graduated from university in the early '90s, got a job, and stayed there. So I'm on my now 27th year with well, originally ATI, but now with AMD. And so I'm glad now. Ruben and team invited me to join TeamRGE a little while ago. We're quite excited about that. Can I get confirmation that
Yeah, I
you're
see
able
your
to see
screen,
my
Joe.
screen?
Yeah. Yep.
Thanks for joining.
Okay.
We're
Full
watching
screen. Okay.
we're watching
Okay,
presenter
great.
mode.
Perfect. So yes, I've been here forever with respect to AMD in the VDI
Joe,
space. Yep.
Joe, we're seeing the presenter mode. We are not seeing the full screen.
Oh, okay. Oh, let me. Where is
Go
that?
to go to display settings and just swap. Yeah, that should work.
Okay. Sorry, give me a sec.
Oh, it should be fine. Like in PowerPoint itself,
In
you can.
PowerPoint.
Yeah, if you just start the presentation, Joe.
Yeah. Where are we?
Start the deck like normal, or start the presentation, and then up on the
Yeah.
top, see where it says display settings in the upper left? You should
There
be
we
able to
go.
click that and say swap display. There you go.
Are we good?
Awesome.
Yes.
Yep, go
Now
for
we're
it.
good.
Perfect. Okay. All right. So for this session, with respect to AMD in this space, obviously Azure NVv4 has been a primary focus of ours for more than a year now, and we're excited to work with Microsoft on that. So what I'm presenting here is kind of a very little quick peek under the hood of basically the GPU partitioning we do with NVv4. Again, it's going to be somewhat high level, so I just want to talk quickly about the instance types, and I think Thomas and others have already shown what those are, but I will quickly go through that. But primarily here, what this session, I just wanted to kind of give a peek at the SRV-based technology that we use with our GPUs for this partitioning that we do. We find that, obviously in the last year or more, various trade shows that we've been involved in, people don't really understand the SRV. I'm not even sure that they need to, but there's some aspects of it that we like to be able to explain to push our mantra of a very predictable performance experience, a very linear scaling of performance across how you partition that GPU. And because of the way we do SRV based hardware virtualization solution, that's why we can do that. Now, in terms of, again, NVv4 with Azure has been, as I said, a big focus of ours. One of the things that Microsoft and AMD like to stress with the concept of why NV4 can work for a lot of use cases, prior to this, any cloud-based virtualized GPU solutions were always, if you needed a GPU, you have to get the full GPU, and that can be pricey at times depending on the size and the instance you're getting. There's even instances out there both across Azure and AWS where you could get multiple GPUs. So we haven't played in that space, but instead we took this approach where the key was to match the right VM resources to each particular user workload type. And we've done a lot of testing behind that. We've had others jump in and do a lot of testing around what we can do there. And in the case of NVv4, just let me review again, this has been presented here very quickly, but these are the 4 instance types available under NVv4. I think we're in 3 regions now. I know US Southwest, US East, and over there in Europe West, I believe. And I don't have the detail of when Microsoft is firing up more data centers and regions with NVv4, but that's definitely coming. And Thomas did allude to a recent problem we had. I can't really talk about the details of what that was, the root cause, and all I can say is, yes, Microsoft. We've worked with Microsoft. It was resolved. I believe the last data center was updated this past weekend. So as of this week, we should be fully up everywhere that NVv4 was previously. And we're glad we got that behind us because, we did interrupt some work that people were doing, and but Microsoft is handling that, and we should be good from here on in. So these are the four instance types and sizes that we offer, or Azure offers with NVv4. I mean, they scale up in terms of, you know, this at the smallest size. It is an eighth of a GPU, so it's a 2 gigabyte frame buffer. And there's 4 virtual CPUs and 14 gigabytes of RAM. And effectively, as we move up to the V4, the V8, the 16, and the 32, we're effectively doubling each of those numbers. So we go from 4 to 8 vCPUs. The frame buffer goes from 2 to 4, which is a quarter of a GPU in this case, and we double the memory, right up to the full size, the 32, which is 32 vCPUs, a full MI25 GPU and 112 gigabytes of RAM. Now, so, and one thing I'll show, I mean, I'm gonna, in a few slides, you'll see, I'm gonna actually kind of go into an example of, you know, how we do SRV and why it's, again, a very predictable user experience or GPU performance experience as you scale up between these sizes. And effectively, you know, if you started up and you fired up a 32 instance and you do some benchmarking, and then you change that, shut down your VM, and change that to a 16 and 8 and then a 4, you very effectively and get a very linear scaling of the GPU performance. And you'll see why that's the case later on. So, so if you get a benchmark score with a 32 size VM, and then you try a 16, you're very effectively going to be seeing half of the GPU performance. And then the same way as you scale down to the 8 and the 4. So behind the NVv4 instance, and again, I am a GPU guy at AMD, so I'm kind of only focused on the GPU here, but I just definitely would like to call out on these, on NVv4, it's a combination of the AMD second generation EPYC processor and the MI25. And, even though I'm a GPU guy at AMD, when the original EPYC came out, we were excited about that. We got some good headway there. But it had its issues. It had its NUMA node type issues, depending when you're doing virtualization, and that was sometimes a challenge. But when they went to the Gen 2 or the Rome-based EPYC, things changed dramatically and remarkably so, and we were all quite excited about that. So having this combination with the Rome EPYC-based CPU and now the AMD Instinct MI25, we're quite excited about that. So the Radeon Instinct MI25, and many of you may be familiar with, on our gaming or Radeon side, we had a Vega 64, Vega 56. So the 64 was effectively a very similar GPU to what we have here. Again, it was named a Vega 64 because it has 64 compute units. It was a 300 watt TDP board. I mentioned there the teraflops we get for floating point 30 Gen 16. It has 16 gigabytes of HBM2 memory, and the feature that we have in this GPU and effectively any data center GPU that we offer in that space, SRV, MxGPU is the technology behind how we do our virtualization. GPU-P is basically the GPU partitioning that Microsoft has integrated with in Azure with Hyper-V that does the splitting up, physical splitting up of the GPU. Also, so on the MI25 a little bit further, again, it's running under Azure with Hyper-V. In terms of remoting protocols, these are the listed ones. Others will work, but these are the ones we effectively test with extensively. So RDP, Citrix ATS3D Pro, Citrix Cloud, and as well as TeamRGE. In terms of graphics drivers, one of the reasons, again, we went with an SRV solution is the driver that we get for, and we qualify and do a lot of testing and release for our workstation brand products out there that have been out there for years. And I think we have like an enterprise quarterly release of a particular enterprise driver from AMD. We're effectively using the same driver in our virtual solutions here. So, if all the optimizations we've had for various, CAD apps, ISV apps that are have been optimized over the years, all the certifications, or the fact that you can run certifications in a virtualized environment, just as we do in bare metal. So that's a key feature. And again, apart from, in the area of in our virtual, when you install in a virtual machine, obviously there's additions within the area of like virtual display technologies that are not going to be there in bare metal, for example. Other than that, it is effectively the same driver. So we definitely take the benefits of that, extending for what we do in our workstation bare metal space right into virtualization. In terms of the OS, NVv4, we support Windows 10 clients as well as Windows 10 multi-session, and then the two versions, 2016 and 2019 of the server OSs. And yeah, and then under 110 EMS and server 16 and 19, obviously we multi-session is kind of the key there. We've done a lot of testing, and we've had RDS Gurus with Benny and Kristen have been doing a lot of testing here. We hope to have results, more likely released from Microsoft than us, but we're quite excited what we're seeing in terms of multi-session support and the user density we could get there. So that will come in time, hopefully sooner than later, and I think it'll provide a lot of good information to the community. And then in terms of graphics API support, anything that we do in our bare metal GPU solutions with the enterprise drivers, so every API, whether it be DX 9 through 12, OpenGL, OpenCL, Vulkan, and then AMD RapidFire, that's the API we use for basically the code encoding acceleration. I will actually use a GPU. Many different, certainly the remoting protocols. Well, Citrix and TeamRGE certainly are taking advantage of that today, and hopefully we'll expand on that, with future products. But in short, every API that we support in that driver on a bare metal product, we support in the virtualized environment. And going into the fact that we're doing SRV, it kind of sheds some light on why we're able to do that. So SRV, it stands for Single Root I/O Virtualization. It's been a industry standard for some time. It's I think based on the PCIe base specs since 1.1, and network interface cards have been using this for many years. We were the first on the GPU side to introduce this as a hardware virtualization solution. But the key fact here is, or information that's pertinent, is we're able to have what they call a physical function, which is the core GPU, or the physical function, or PF, as well as virtual functions, a VF. So, in later slides, there'll be a VF reference every once in a while, just so you understand what that is. So it's a virtual function. It is a PCIe device, like when our host driver is installed in a hypervisor, and we enable however many virtual devices on this physical PCIe graphics, we're able to pass through that virtual function, and the OS, or the virtual machine, effectively sees it as a pass-through PCI device, and it really treats it no differently. We just happen to set that up on the host side, and we're able to pass through to the virtual machine across the hypervisors we support. And one important other aspect of SRV is that we're able to, in the same way as a physical device where the PCI configuration space has all the attributes of the card, all the capability structures, all of that. In our MI25, for example, we have the PCI configuration space defined as well for all the virtual functions. So I'll show you in the next slide. It makes it a little bit more clear. So again, typical representation of this, in fact, the extension part for SRV that's added in the PCI config space for our data center GPUs. So apart from, we also obviously have all the frame buffer, physical address space that's carved out. We also have the virtual function configuration spaces, and also the frame buffers, the I/O bars, the memory mapped I/O bars. All of that is replicated in the GPU, and so that is the reason why when we actually are able to define and set up a virtual function so it's visible on the bus and visible to the hypervisor, and pass it through the VM. Even our graphics driver that's running in that VM, I don't say that does not know that it's a virtual function, but it treats it no differently. And this representation kind of shows that a little bit more. So this is a kind of a system view of a scenario where we have a physical host and hypervisor. You have the physical, the PF device, as we call that, on the left, and the the AMD GPU host driver, GPU V is the name of what we give the host driver. So it's obviously doing one directly communicating with all the different base address registers, whether, again, memory mapped.io or the configuration registers, the actual memory bar, which is the frame buffer. So it does all that communication. So, but in the VMs themselves, so if you look at VM0, again, we run the same native GPU Windows display driver as we do in bare metal. And that virtual device, the virtual function that's passed through to that VM, it sees its own bars, its own MMIO, its own memory, its own frame buffer, and basically, and each VM is passed through a virtual function. And within that VM, it is a very much a self-contained virtual system. With SRV, we carve out a certain amount of frame buffer per virtual functions. And then again, the virtual functions themselves have access to all the GPU when that virtual function gets its time in what we call, it's a time slicing concept, and something I'd like to show in a sec. So this is a kind of very high level. I was hoping to go a little deeper on, some of the concepts we use in our scheduling as we cycle through virtual functions, but at a higher level, I didn't want to go too deep into the weeds. Obviously, I can't reveal too much what we do there, but the concept with SRV that I want to invoke here is that each virtual machine is given an amount of time so each VM is given an amount of time on the GPU engines, and when that virtual function has exclusive access to the full GPU, and it has access to all engines given in its given time slice. So the time slice concept is it's something that's programmable, and it's not dynamic. We will set it for a given GPU for a given solution. We set a fixed time interval in the AMD host driver, and we determine, obviously at the beginning of development on a given new GPU, as we do testing, we'll do a bunch of physical testing of various different time slices across various different workloads, and we'll pick an optimal one. It gets a little bit hairy if we try to dynamically change that depending on workload, and that, so we don't do that. It's a fixed, although programmable, it is a fixed variable. So also here I'm showing a very kind of simplified example of, in this case, we have imagine the MI25 is split into 4 partitions. So it's a full 16 gig frame buffer. So each partition gets 4 gigabytes. It gets a tad less because there's some context there. We have to save some stuff, but it's just shy of 4 gigabytes in this example. And I picked 5 milliseconds because the math is easy with 5 milliseconds. I'm not even sure if that's what we're using on NVv4 today. I don't exactly remember what that was. But the way the time slicing works is, so in this case, we have 4 virtual machines, 4 virtual functions, each single one passed to a virtual machine. So when things kick off, so for the first 5 milliseconds, that first VM that has the virtual function 0 passed through it, it has full exclusive access to that full GPU, all the engines, at every APL level, it has that for 5 milliseconds, sorry. And then there's a context switch, or we call the world switch, and a bunch in this GPU, a bunch of registers or pointers are changed to the other different VF spaces and register spaces, and there's a context switch, and the next VM or that next VF gets the full GPU for into the next 5 milliseconds, and so on. But if you look at that original VF0 and VM0, once it was done with its 5 milliseconds, it processed whatever jobs were in the queue there. It then basically goes idle, and it waits for effectively 15 milliseconds till it gets access again. And if you look at this, it's a little bit easier to understand why the performance across, as you do the splits of GPU from the full to the half to the quarter to the eighth, it's very predictable. As I said, again, for example, in this case, we split a GPU into 4. If we split a GPU into 8 instead, it's still a 5 millisecond window it gets to do its job, and then it waits. In the case of if we split 8 ways, it's going to be waiting 30 milliseconds before it gets its next access to the full GPU. So the performance, again, very predictable. As I said earlier, going from the full GPU to the half. You're effectively going to be getting half the performance if you're doing any benchmarking. It is exactly what you're going to be seeing.
Hey, Joe, just a quick time check. You got about a minute left.
Okay,
Don't want to stop the geek out, but
I am pretty much. This is pretty much done. So again, just a graphical representation. In a typical GPU sharing scenario, whether it's something like it was VMware's VSGPU or whatever they call it, the sharing graphic concept. As you add more users, the graphics performance definitely is going to be affected. But with our MxGPU solution, and these are actually some results we did across various workloads. Many of those are from SpecView for 13, I believe, and a few others like 3D Mark. But whether it's one active user or 4 active users, performance effectively stays the same. Now there are some variations there because depending on the workload, those time slices, there are some scenarios with our algorithms that do alter a slight bit. So you are going to have some slight variations, but very much so that's what you're going to see. And just a very last quick thing, I just wanted to mention with NVv4, we have been working on some ISV certifications. I just wanted to let the community know. So far, we have Autodesk, so Revit, AutoCAD, and Inventor are certified. If you go to basically their HCL with Autodesk, you'll see the NVv4 instances are available there. We are certified there. We also have Azure ArcGIS did a bunch of testing, and they gave it a blessing. They have a blog out for that. And we are working on more. And that'll come, and as we get more and more, we'll have some releases out to the community about what we've done. So
awesome.
That's it.
Thanks, Joe.
All right. Thank you.